Welcome back to our series on ellipses, and in this video we're going to look at the eccentricity of a planet's orbit. So for fun, we're going to look at Pluto, and these numbers are approximations, but they're not too far off. So the planets, they actually move around the sun in elliptical orbits. It's not really circular, but it's close for Earth and for most planets. But however, Pluto is pretty elliptical at its what we call the perihelion. It's actually pretty close to the sun, and believe it or not, the sun is at one of the foci. The sun is at a focus of an elliptical orbit of the planets, including Earth's, right? And then there's nothing at the other focus, but the perihelion is the point at which the planet is the closest to the sun, a little distance right in there. And the aphelion is the point at which that planet is furthest from the sun. This is drawn to be a pretty extreme example, but you can see pretty clearly, and I think for Pluto, it is actually somewhat accurate, that it's pretty eccentric. Pluto actually has an eccentricity of 0.24, right? So it's the most eccentric, if you count it as a planet at least, of all of the planets in the solar system. So what we know about it right here, what we know is that the length of the minor axis is approximately 11 billion kilometers. That's the minor axis. Remember, the minor axis goes from here all the way down to here. So we know that that whole length is 11 billion. We typically call half of that length B. So that means the total length of that, which would be 2B, is 11 billion. We're going to switch to scientific notation in just a moment so that we don't have to write out all those zeros. All right, so given that length and of the minor axis and the eccentricity, can we find the distance between Pluto and the sun at the perihelion and the aphelion? And I bet that we can. All right, so what do we do, right? Well, let's analyze what we know. We can solve for B fairly quickly. We just divide both sides of this by 2. That's going to give us 5.5. If we switch to scientific notation, would be times 10 to the, if you count that over, that's going to be times 10 to the 9th. All right. We don't really need the equation of the ellipse. We just need to find C, because C here, let's draw C on here. C is at where the focus is, that distance from the center to the focus, that is C. And the distance from the center all the way to the planet at either of those endpoints, the vertices, right? That is called A. All right, so what we know here, what do we know? We know the relationship between A, B, and C for ellipses is equal to C squared is equal to A squared minus B squared. Well, we only know one of those, right? We know B, we just found is 5.5 times 10 to the 9th kilometers. But we also know the eccentricity, and in a prior video, we learned about how the eccentricity is the ratio, 0.24, is equal to the ratio of C to A. So we really have two equations here that we can use, both involving C and A, so we can solve for both C and A. So the simplest way to do this one would be to eliminate the fraction. So if we multiply both sides of this equation by A, what we're going to get is that 0.24 times A, that's a 0.24 times A, is equal to C. And since I'm interested in solving for, well, I know B, since I'm interested in solving, I'm going to substitute this in here into this blue equation so that we can relate A and C, right? So C is equal to 0.24A. Let's plug that in right here into C squared. So that will give us 0.24A all squared is equal to A squared minus B squared. But we know now that B is 5.5. That's a point there, times 10 to the power of 9. Now we have an equation for which we can solve for A. It's all A's, right? So we're definitely going to need a calculator for this. So what we're going to do is pull out our handy dandy TI-84 here. We're going to do some calculations. So first I'm going to square 0.24. So 0.24 squared is equal to 0.0576. So I'm going to write that here on the left. Squaring both the 0.24 and the A gives us 0.0576 A squared on the left. oops, and I left a square off of that b squared there. That would also be squared, right? Equals to a squared minus. Now, since we're multiplying the 5.5 and the 10 to the ninth, the simplest way to do this would be to square both of those numbers. So let's go ahead and square 5.5. 5.5 squared is 30.25. So that's going to be 30.25 times 10 to the power of, well, 10 to the ninth all squared. We would multiply those exponents to get 10 to the power of 18. All right, continuing simplifying, I'm going to actually add this number to both sides and subtract this number from both sides here in one big fancy step, right? That'll give us positive 30.25, and I could probably move the decimal over 1 and all that, but it's fine how it is right now. So 30.25 times 10 to the 18th on the right is equal to 1a squared. Let's go ahead and write that out. 1a squared minus 0.0576a squared. So since those are like terms, we can go ahead and subtract those numbers to get 30.25 times 10 to the 18th is equal to, we need to do 1 minus that 0.0576 number. We can go up and reuse that number. We get 0.9424. So that's going to be the coefficient of a squared here on the right. So we're going to have 0.9424a squared. Well, we're solving for a, so we're going to divide both sides of this whole equation by 0.9424, which I'm going to do on the calculator here. So we're going to take the 30.25, I'll just go back up and re-hit that, which is times 10 to the 18th. So I'm going to put times 10 to the power of 18, and we're going to divide that by the 0.9424, and that's going to equal a squared. So we get this giant number, 3.20988, that's scientific notation, times 10 to the 19th is equal to a squared. Let me write that down, just an approximation for that, and then we will square root both sides of that to solve for a. So dividing both sides by, maybe I should show that, 0.9424, right? 0.9424 all over 0.9424 gives us, let's see, I'm going to flip this around and put the a squared on the left, right? We get a squared is approximately equal to, the calculator had said 3.20988 times 10 to the power of 19. Now we're going to square root both sides of that equation on the calculator and go see what we get. So we're going to take the square root of the above number, just highlight it, there we go, hit enter. All right, and we get that nice number, which is long, but okay. So I've got that written down here. It's going to be, these are the digits. I'm just going to read them as we go. So 566, 5588, 798. Okay, kind of working backwards there. Put a comma after every 3. We see, okay. So it's 5.6 billion or so, right? So there's A. All right, now we've got the value of A. Now, in order to find the perihelion and aphelion, that's either equal to A minus C, that's your perihelion. It's the distance from the focus to the sun, which is, see the green A here. If we go that distance and we take away the C, the distance from the center to the focus, we will have the distance from the sun to the perihelion. Or we add the length of the half the length, which is A of the major axis, to the focus. So to go all the way from the aphelion way over here to the sun, we're going to do A plus C. So point is, we still need C. Right here at the very top, you can see up that C is equal to 0.24 times A. So I'm going to go back to that equation right there. C is equal to 0.24 times A. Let's put that over here. So C is 0.24 times that number, 5,665,588,798. There we go. And we can approximate that on the calculator. So we can do that prior number times 0.24 gives us that number right there. Okay, I'm going to write that down here. That said The digits, just reading them across, are 135,974,1312. Okay, kind of working backwards here. We see, okay, it's a little over a billion, right? So let's write out what I was saying earlier, right? So the perihelion, that's the closest it gets. Perihelion would be equal to A plus C. So if we add those two numbers, A and C, A is the 5.6 billion, C is the, I'm sorry, minus, right? Perihelion is the closer point, right? So let's do minus C. Almost got those backwards. Whoops. A minus C, right? So let's subtract those two numbers. We're going to just reuse the numbers. Oops, goodness. No, 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 no. We're going to go back here. So I go up and subtract that. There we go. And we get, that's the closest that it gets, right, to the sun is, okay, let's write this out. So 4, comma, 305. This is pretty precise. It's probably not quite that accurate, comma, 847, comma, 486. Of course, that's not, it's too accurate, right? We can't have that many significant digits. But anyways, we can definitely say that it is about 4.3 times 10 to the power of 9 kilometers. All right, so that's the closest that Pluto gets to the sun. Now let's go ahead and find the aphelion, which would be the sum of A and C. So let's see what we get for that. We're going to add the 5.6 plus the 1.3 billion. So going up here, this time we're going to hit that plus that number, and we get about, there we go, it's about 7.03 times 10 to the ninth. Let's write that little number out just for fun here. So 70, where is it? 702, 5, 7, comma, 025, comma, 330, comma, 110, which is a little too precise, but we can say it is approximately 7.03 times 10 to the ninth kilometers at the furthest point from the sun. Isn't that fun?